Over the years, jet engines have been the driving force behind modern aviation's incredible progress and achievements. These remarkable devices have enabled us to transcend the boundaries of time and space, connecting distant corners of the globe in hours, tracing their evolution from the early days of aviation to the cutting-edge innovations that promise to shape the future of air travel. Join us as we explore the US's new hydrogen jet engine that makes the Darkstar hypersonic. The typical jet engine's inner workings are pretty fascinating. It all starts with the compressor, like a set of fans that squeeze air into a smaller space. This makes the air pressurized and super hot. Next, this super hot and pressurized air goes into the combustor, where it meets some jet fuel, and they mix. When they ignite, it is like a big explosion, releasing energy. This energy makes the air expand quickly and rush out of the back of the engine. But here is where it gets even cooler. The hot air passes through a turbine as it is on its way out. This turbine is like a clever device that grabs some of the energy from the hot air. It uses that energy to power the fans in the front and keep the whole process going. After giving some of its energy to the turbine, the rest of the hot air zooms out of the back of the engine like a powerful jet. This speedy jet of hot air pushes the airplane forward, making it fly through the sky. So in simple terms, the engine starts by squishing air, mixing it with fuel to make a big explosion that keeps the plane moving in the air. The story of this mind-blowing innovation began in the early 20th century, when aviation was taking its first tentative steps and the limitations of traditional piston engines were becoming increasingly apparent. These engines, which relied on the repetitive motion of pistons, had reached a point where they could no longer deliver the speed and performance that aviators and aircraft designers envisioned. Sir Frank Whittle, a British Royal Air Force officer, and Dr. Hans von Ohain, a young German engineer, entered the limelight. In the 1930s, both of these visionary individuals independently conceived the concept of a jet engine, driven by the idea of harnessing the inherent power of jet propulsion to propel aircraft forward. Sir Frank Whittle, born in 1907, was a brilliant engineer and pilot who had long been fascinated by the idea of a jet engine. His insights and understanding of gas turbine technology led him to draft the first patent for a jet engine in 1930, while he was still a cadet at the Royal Air Force College. Whittle's concept involved drawing in air, compressing it, mixing it with fuel, igniting the mixture, and expelling the high-speed exhaust gases to generate thrust, the basic principles of jet propulsion. Despite skepticism and bureaucratic challenges, Whittle's dedication and belief in the potential of his idea were unwavering. Across the English Channel, Dr. Hans von Ohain was independently working on a similar concept in Germany. Born in 1911, von Ohain was a brilliant engineering student who, by 1935, had formulated the design for a jet engine that operated on similar principles to Whittle's concept. While the two inventors were separated by distance and circumstance, their shared vision for the future of aviation was unmistakable. In 1937, Sir Frank Whittle's relentless pursuit of his dream culminated in a groundbreaking achievement, successfully constructing and testing the world's first operational jet engine. This monumental milestone marked the beginning of a new era in aviation, one that would fundamentally alter the course of human flight. Whittle's jet engine, known as the Doody-U or Whittle unit, was a remarkable piece of engineering. It consisted of a centrifugal compressor, a combustion chamber, and a turbine, all meticulously designed to convert the energy from burning fuel into forward thrust efficiently. The engine's successful test runs demonstrated that jet propulsion was not just a theoretical concept, but a practical reality. The successful development of the jet engine by Sir Frank Whittle and Dr. Hans von Ohain was a breakthrough in aviation. Gone were the days of piston engines struggling to push aircraft to their limits. A new era had dawned, one defined by jet propulsion's immense power and potential. The advantages of jet engines were immediately noticed. They offered significantly higher thrust-to-weight ratios than their piston-driven counterparts, resulting in faster and more agile aircraft. Jet engines eliminated the need for propellers, reducing drag and enhancing aerodynamic performance. These engines also operated more smoothly, providing a quieter and more comfortable flying experience. As the world was on the brink of World War II, Britain and Germany recognized the strategic importance of jet propulsion in military aviation. The British Ministry of Aircraft Production established the Power Jets Limited Company to develop and manufacture jet engines based on Whittle's designs. In Germany, Dr. von Ohain's work led to the development of the Heinkel Hy-178, the world's first jet-powered aircraft, which made its historic flight in 1939. Before World War II, aerial warfare primarily relied on propeller-driven aircraft. These aircraft were limited in terms of speed, altitude, and maneuverability. The war's combatants, including major powers like Germany, the United States, and the United Kingdom, recognized the need for more advanced and faster aircraft to gain a strategic edge. The Messerschmitt Me-262, also known as the Schwalbe, emerged as one of the most iconic aircraft of the era. Jet engines powered the plane. The Me-262 dramatically differed from conventional piston engine fighters. The Me-262's turbojet engines, specifically the Junkers Jumo 004 and later the BMW 003, propelled it to previously unthinkable speeds, capable of reaching speeds of around 850 kilometers per hour, outpacing all contemporary Allied fighters. Its operational debut in 1944 sent shockwaves through the aviation community as it became clear that a new era of aerial warfare had arrived. The speed and agility of the Me-262 gave it a distinct advantage in combat. It could easily intercept and engage Allied bombers, making it a formidable adversary in the skies. While its impact on the war's outcome was limited due to production challenges and logistical constraints, the Messerschmitt Me-262 demonstrated the immense potential of jet-powered combat aircraft. The Gloucester Meteor, Britain's response to the Me-262, became the first Allied jet fighter to enter operational service. Its Rolls-Royce Welland engines propelled it to speeds that rivaled contemporary propeller-driven fighters. After World War II, the innovation and development of jet engines took a significant turn as they transitioned from military applications to commercial aviation. This transition would pave the way for a new era in air travel characterized by higher speeds, enhanced passenger comfort, and reduced travel times. A key milestone in this transition was the introduction of the de Havilland Comet in 1952, the world's first jet-powered commercial airliner. The de Havilland Comet, a British creation, emerged as the pioneer of commercial jet travel. It debuted in 1952, representing a monumental leap in aviation technology. This sleek, cutting-edge aircraft was powered by 4 de Havilland Ghost turbojet engines and boasted a pressurized cabin for passenger comfort at high altitudes. While the Comet represented a significant airline investment, it quickly proved its economic viability. Its efficiency and speed translated into reduced operating costs and increased revenue potential. Airlines that embraced jet technology gained a competitive edge in the industry. Passengers preferred the speed and comfort of jet travel, and airlines that could offer these benefits captured a larger market share. Despite its groundbreaking achievements, the de Havilland Comet faced its share of challenges and setbacks. In the early years of operation, a series of tragic accidents involving Comet aircraft raised concerns about its structural integrity. Investigations revealed design flaws related to the aircraft's square-shaped windows and stresses during pressurization cycles. These issues led to catastrophic accidents and a loss of public confidence in the aircraft. The de Havilland Company redesigned the Comet, addressing the structural concerns. However, by this time, other manufacturers, notably Boeing and Douglas in the United States, had entered the commercial jet market with their offerings. In 1958, Boeing introduced the 707, a long-range jetliner that would become an icon of commercial aviation. Around the same time, Douglas unveiled the DC-8, another formidable contender in the growing market for jet-powered airliners. These American-made jetliners quickly gained widespread acceptance and trust among airlines and passengers. The Boeing 707, for example, offered a range of configurations and seating arrangements, making it versatile for various airline needs. With its four powerful turbojet engines, the 707 could easily cover long distances, making it suitable for transcontinental and intercontinental flights. The success of these early jetliners spurred significant advancements in jet engine technology. Engine manufacturers like Pratt & Whitney, Rolls-Royce, and General Electric competed to develop more powerful and efficient engines. These advancements resulted in engines with higher thrust-to-weight ratios, reduced fuel consumption, and improved reliability. The change from turbojet engines to turbofan engines marked another significant milestone in aviation history. The technological shift laid the foundation for contemporary jetliners, seamlessly merging the advantages of jet propulsion with the efficiency reminiscent of a propeller. Turbo engines, including turbochargers in internal combustion and turbofan engines in aviation, offer several distinct advantages that have made them widely used in various applications. Turbochargers in internal combustion and turbofan engines in aviation significantly enhance power and efficiency. In internal combustion engines, a turbocharger forces more air into the chamber, allowing for better fuel combustion and increased power output. This results in improved acceleration and overall performance without needing a larger engine. In aviation, turbofan engines are known for their fuel efficiency, allowing aircraft to travel longer distances with less fuel consumption. This efficiency is particularly crucial in commercial aviation, where fuel costs are a significant operational expense. Turbo engines also excel at higher altitudes where air pressure is lower by maintaining their efficiency and power output at high altitudes, allowing aircraft to cruise at more fuel-efficient levels. This capability is crucial for long-haul flights, where staying at optimal cruising altitudes reduces travel time and fuel consumption. Similarly, turbocharged internal combustion engines perform well at high altitudes, making them suitable for mountainous terrain and high-altitude driving applications. Turbo engines enable downsizing while maintaining or even enhancing performance. In the automotive industry, smaller turbocharged engines can replace larger naturally aspirated ones without sacrificing power. This downsizing reduces weight, contributing to better fuel efficiency and handling characteristics. In aviation, turbofan engines provide the required thrust with smaller and lighter engine cores compared to older turbojet designs. This weight reduction benefits aircraft, allowing for increased payload capacity and improved overall performance. These engines often result in reduced emissions. In internal combustion engines, turbocharging can help improve fuel efficiency, leading to lower carbon dioxide emissions. Additionally, turbocharged engines can be downsized, further reducing emissions. In aviation, modern turbofan engines are designed to focus on environmental sustainability. They produce fewer emissions, including lower levels of CO2 and nitrogen oxides, compared to older engine types, helping to mitigate the aviation industry's environmental impact. Their large front fan defines them and has become the standard for modern aircraft due to their impressive efficiency and quieter operation. In this transformation, we explore the essence of turbofans and the aircraft that embraced this groundbreaking technology. At their core, turbofan engines comprise intricate components working in harmony to generate efficient thrust. These include the compressor, combustor, turbine, and prominent fan, setting turbofans apart from earlier turbojets. The process commences with the fan, which draws in and compresses large volumes of air. This fan is a complex assembly of nested smaller fans, elevating the air's pressure and temperature and laying the foundation for engine operation. The pressurized air enters the combustor, mixing it with jet fuel and igniting it, creating a controlled explosion that releases substantial energy. This energy causes rapid air expansion, propelling it towards the engine's rear. The brilliance unfolds as the hot, high-speed air passes through the turbine, which captures some of its energy. This captured energy powers the fan and compressor, maintaining engine efficiency. The remaining hot air exits the engine, forming a potent air jet and propelling the aircraft forward. The type of turbofan engine commonly used in modern commercial aviation, high-bypass turbofan engines, has risen to prominence as the standard power plant for passenger aircraft. They are a marvel of engineering that leverages the principles of jet propulsion with a unique twist. A substantial portion of the incoming air bypasses the core engine, contributing to thrust generation while also serving as a noise reduction mechanism. The bypass ratio is a critical parameter that defines the engine's efficiency and noise characteristics. It represents the ratio of air mass that bypasses the core to the mass of air that passes through the core. High bypass engines have a bypass ratio typically exceeding 5:1, meaning that more than 5 times the amount of air flows around the core compared to what flows through it. Two standout examples of high bypass turbofan engines that have significantly impacted the commercial aviation industry are the General Electric CFM56 and the Pratt & Whitney PW1000G. The CFM56 engine family, developed by CFM International, has been a workhorse in commercial aviation for decades. Renowned for their reliability and efficiency, CFM56 engines power many aircraft, including the Boeing 737 and Airbus A320 families. These engines have played a substantial role in making air travel accessible and affordable to millions worldwide. The PW1000G is a groundbreaking engine known for its innovative geared turbofan technology. This design incorporates a reduction gearbox between the fan and the low-pressure compressor, allowing each component to operate at its optimal speed. The result is increased fuel efficiency and reduced noise. Aircraft like the Airbus A320neo and the Embraer E-Jet E2 series benefit from the PW1000G's performance and eco-friendliness attributes. The geared turbofan concept represents a significant leap in jet engine technology and is a testament to the ongoing pursuit of efficiency and sustainability in aviation. While subsonic commercial flight is the norm today, supersonic travel was once a reality, as exemplified by the Concorde, which operated at twice the speed of sound. Despite its technological prowess, the Concorde faced economic challenges and retired from service. The quest for even faster air travel continues with hypersonic engines, where aircraft can reach speeds exceeding Mach 5. Innovations like scramjets and combined cycle engines are discussed, offering a glimpse into the future of rapid, long-distance travel. One standout example is Pratt & Whitney's F135 engine, which powers the F-35 Lightning aircraft. This engine design is special because it combines a high-power turbofan with a low bypass ratio, producing an impressive 43,000 pounds of thrust. The F-35 comes in 3 versions, one for regular takeoff, one for short takeoff and vertical landing, and one for carrier-based operations. The carrier-based version has added features like enhanced maneuverability for takeoffs and landings on aircraft carriers. The F135 engine is smartly designed with a high-pressure single-stage fan, a 6-stage compressor, and a unique counter-rotating turbo setup. This design boosts power while saving fuel, making it more efficient than older engines. The F135 also has a conventional afterburner, allowing the F-35 to go supersonic without using the primary combustion chamber. The engine is built to last, with turbine blades made from strong materials that can handle high temperatures and pressures, protected by a special coating. Moving on to the successor of the GE J85 engine, which is currently in development as a turbine-based combined cycle engine, it embodies a blend of sophistication in design and exceptional performance. This innovative engine, known as the Chimera, is set to power the Quarter Horse, a remotely piloted high-speed aircraft. Its hybrid approach sets it apart, incorporating elements from turbojet and ramjet engines. Remarkably, the turbojet component can function even when the aircraft is stationary, facilitating takeoff and lower-speed flight. As the aircraft accelerates, it seamlessly transitions into a ramjet configuration, known for its efficiency at high speeds, especially when the aircraft surpasses the speed of sound by multiples. This dual-mode operation distinguishes the Chimera from conventional jet engines, which typically operate in a single mode. Notably, the Chimera engine and the quarter-horse aircraft are constructed using high-temperature materials capable of withstanding the extreme heat generated during high-speed flight. In 2021, the Air Force awarded Hermeus a $60 million contract to develop 3 uncrewed concept aircraft, including the hypersonic Quarter Horse. As of late November 2022, Hermeus had completed the production of its hypersonic engine, bringing this groundbreaking technology one step closer to reality. Still on the quest to develop more fuel-efficient and environmentally friendly engines, topics like using alternative fuels, advanced materials, and cutting-edge engine designs to reduce emissions and carbon footprints are being discussed. The aviation industry is exploring electric and hybrid propulsion systems as potential game changers. Electric and hybrid propulsion promises quieter, cleaner, and more sustainable air travel. Operating on the same fundamental principles as traditional jet engines, hydrogen jet engines face unique challenges. Hydrogen, in liquid form, is much denser in energy but requires extremely low temperatures to remain a liquid. To address this, the hydrogen jet engine incorporates a highly insulated tank with an integrated cooling system, maintaining hydrogen as a liquid at a bone-chilling negative 423 degrees Fahrenheit. Safety measures include multiple systems to prevent sparks or flames from reaching the hydrogen fuel, with rapid shutdown capabilities in case of a leak or malfunction. One of the latest hydrogen jet engines in production is the F-130 dual-pod engine by Rolls-Royce, chosen by the U.S. Air Force to power their B-52 Stratofortress bombers. This engine offers impressive fuel efficiency, boasting around 30% better fuel economy than its predecessors and requiring fewer maintenance hours. Moreover, it mitigates emissions, specifically nitrogen oxides, a significant contributor to air pollution. Nevertheless, a substantial challenge remains in establishing manufacturing facilities capable of producing these engines on a large scale. The manufacturing process for jet engines is intricate, involving advanced materials, precision machining, and automation. Each component is meticulously crafted to withstand the extreme conditions of operation. Rigorous testing ensures the engine's reliability and performance by subjecting it to demanding conditions, including extreme temperatures and pressures. With comprehensive testing procedures underway for each of these jet engines, their introduction into practical aviation is imminent. As we gaze towards the future, the continual development and refinement of these technologies promise to redefine the possibilities in aviation, ushering in an era of enhanced efficiency, power, and sustainability in flight. Thank you for watching. While you are still here, click the link on your screen to check out more of our videos. See you there.